So let's get a start on capacitors. Here's an example of one. It's just, this is usually what they tend to look like, just this cylindrical sort of box with a couple of wires sticking out. I've got this one mounted on a wooden block with a couple of nails to make it easier to attach stuff, but it's just this object with a couple of wires sticking out. But what's going on inside is typically you've got two metal plates. Two usually pretty large metal plates, although in this cylindrical version, they're also sort of coiled up on themselves to fit into a smaller space. But in general, a capacitor is just two large lumps of metal, usually plates, with a wire coming out of each one and a separation in between. The earliest examples of capacitors were what's called a Leyden jar, which is literally just a glass jar with a metal coating on the inside and a metal coating on the outside, and a wire or a metal bar coming up out of this one. So notice that this is still a metal plate and a metal plate that's separated. The two metal plates are not touching. So this is a capacitor. The earliest deliberately built example of a capacitor. And now they're made in much smaller, made into a much more compact space. Just two very thin, flat metal, almost you might say metal ribbons coiled up on each other. But the important thing is two pieces of metal separated by a resistor, not in a resistor, separated by a layer of material that does not conduct electricity, an insulating layer. The important thing is charge cannot jump from one plate to the other. So if you were to set this up with, let's say, a battery, and let's say we have a resistor, because even if we don't deliberately build in a resistor, even the wire itself has a little bit of resistance, just a very small amount. So we've got the positive terminal here, we've got the negative terminal here. You could think of this in terms of voltage. Over on this side, we've got a 0 volt region. The battery adds epsilon. Let's say epsilon is, let's say we're using a 9 volt battery. Then over here, we've got a 9 volt region. What would you expect a difference in voltage to do? If you ignore the capacitor for the moment, if you just had a battery and a resistor, yeah, the voltage difference from the battery causes a voltage difference across the resistor, and so you get charge flowing, you get current. And typically, if we just had a gap here, if this circuit was drawn like this, the fact that there's a gap here, what would that do? If you have a gap, what would you expect to happen? Right, there would be no current at all. It stops the flow because there's no complete path. There's no path, there's no circuit for the charge to flow through. But if you have these large metal plates, that changes things, because a large metal plate has lots of space to accept extra charge. Or in the other direction, you could say it has a lot of charge it can donate. Because this plate, it's neutrally charged. We're assuming it's neutrally charged to begin with, but neutrally charged doesn't mean it contains no charge. Neutrally charged means it contains an equal number of protons and electrons. So neutrally charged just means it contains an equal amount of positive and negative charge. Lots and lots of protons, equally lots and lots of electrons. And when we say we're charging something, like how do you make something have negative charge? You could give something negative charge by removing positive charges, but keep in mind where in the atom are the positive charges located. And yeah, really you could do either. In theory, you could give an object negative charge by removing some of the positive charges or adding some negative charges. But where in the atom are the positive charges located? Right, the electrons, which hold the negative charge, are able to move around, at least in metals. The protons usually are not moving. So the positive charges physically are most likely going to stay where they are. There are a few exceptions, but in most of the cases we're dealing with, the positive charges stay where they are. The electrons, the negative charges, are able to move around within a metal. So when we say something is gaining negative charge, we mean we're adding more electrons. When something is gaining positive charge, that means we're removing electrons. A positively charged object is just an object that is missing some electrons. And since these are large metal plates, they've got a lot of electrons they could gain and still be relatively stable. And they've got a lot of electrons they could lose. So these plates could gain extra charge, they could lose charge, and still exist. So these metal plates make a difference. If you just got a gap here, no current can flow. But if you've got these metal plates that can absorb lots of extra charge, then charge can still flow. It just no longer becomes a steady state system because you get charge building up on the plates. As current flows, what's going to happen is you get charge building up on the plates. Specifically, the positive end of the battery, even though it's really electrons coming into the positive end, you could think of it as positive charge leaving the positive end, even though the positive charge isn't really what's moving. But mathematically, positive charge moving one way and negative charge moving the other way are equivalent to each other. So we tend to think of current as the motion of positive charge in some direction, even though physically what's happening is electrons are moving in the other direction. But if you think of it as positive charge moving this way, positive charge starts to accumulate on this plate. And as positive charge leaves, you start to get negative charge accumulating on this plate. So the plates, since they are large metal plates, they can hold extra charge of either type, positive or negative. So as current flows, you get more positive charge building up on one plate, more negative charge building up on the other plate. And current still counts as flowing. Even though no charge can cross this gap is impenetrable to charge. You get charge flowing in one side and a different but equivalent piece of charge flowing out the other side. So this still counts as continuity of current. Any questions on that so far? Now where this gets interesting is it's not just a steady state flow. This is not going to keep flowing forever. Let's say you have one bit of charge, and even though it's negative charge moving this way, electrons moving this way, we can treat it as positive charge moving this way mathematically. So let's assume we've got a little piece of positive charge. The battery, the positive terminal of the battery is trying to push it this way. But there's already some positive charge on the plate. So what's the positive charge on the plate going to do to this positive charge that's trying to be pushed towards it? Right, the positive charge that's already there is going to repel the positive charge that the battery is trying to push in. So we get some pushback. Presumably, it's still going to be moving towards the plate if the push forward from the battery is stronger than the push back from the charged plates, the capacitor. But it's going to get weaker and weaker because the battery is staying the same strength, the same electromotive push, the same 9 volts. But the capacitor's push back is getting stronger and stronger as it gets more and more charged. The more charge the capacitor accumulates, the stronger the pushback becomes, and the weaker the current flowing into it becomes. But what do we call, I mean, if we're saying the capacitor is pushing back, what do we call an electrical push? Yeah, that's the EMF of the battery, or more broadly, the idea of voltage. The fact that the capacitor is pushing back means we have to treat the capacitor as having a voltage of its own. So we're going to have a DeltaV capacitor. Much in the same way that we had earlier, DeltaV from a battery is just a positive constant. And DeltaV from a resistor is proportional to current, negative IR. We're also going to have a DeltaV for a capacitor. And to get this DeltaV for the capacitor, what is it about the capacitor that allows it to push back in the first place? Why is the capacitor able to push back against the current? Yeah, it's charged. And the more charge it has, the more pushback you get. And it turns out we can say these are proportional. The delta voltage for the capacitor is proportional to the charge stored on the capacitor. If you've got a certain amount of charge stored on this capacitor, it acts almost like a battery with a certain voltage. If you store twice as much charge, you get twice as much voltage, twice as much pushback. And I say only sort of like a battery because a battery provides a constant voltage, whereas a capacitor provides a voltage that changes depending on how much charge it stores right now. And that's exhaustible. The capacitor is going to diminish. If you drain the capacitor, if you allow the charge to flow out of the capacitor, then the voltage is going to get weaker and weaker until it runs out of charge. Whereas a battery is going to keep applying the same voltage for a very long time until the chemicals inside it that are powering the reaction run out. For our purposes, effectively almost forever. But the capacitor is going to lose voltage if it loses the charge, or gain voltage if it gets more charge. And if we're saying these quantities are proportional, we can say that one of them equals something times the other. And specifically, we can say, one way we can write this is that the charge stored equals some constant times the delta voltage. And you could think of this almost like a conversion factor. You apply a certain amount of voltage from the battery to the capacitor is going to be able to build up a certain amount of charge. The more voltage you apply, the more charge builds up. Correct. This Q has nothing to do with heat. This Q represents charge. I think the reason they use Q is that it originally stood for electrical quantity. They knew there was something flowing in the circuit, but they had no idea what it was. So they just called it electrical quantity. And these days we call it charge, but we still use the variable Q to represent that charge, that quantity. So yeah, this is the charge stored on the capacitor. So we should expect that since the charge and voltage are proportional, we should expect that the stored charge equals some constant times the voltage. And that constant is called the capacitance, written as a capital C. And you could think of capacitance as almost like a measure of how efficiently the capacitor stores charge. If the capacitor has a very high capacitance, that means it can store a lot of charge with even just a little bit of voltage from the battery. Whereas a very low capacitance, it takes a lot of voltage to store a little bit of charge. So that's how I usually think of it, a measure of the efficiency of the capacitor, how good it is at storing charge in terms of how much voltage it takes. So large capacitance means you can store a lot of charge with just a little bit of voltage. Any questions on how we define that so far? And a couple other ways we could look at that. Since we just introduced a new constant, it's a new multiplier sort of variable thing. It's a good idea to try solving for that, see what it actually means. You solve for C, you just divide by delta V, and you get Q over delta V. So that's how much charge you store. It's the ratio of how much charge gets stored per volt that's placed across it. Again, a measure of efficiency. And you could even get the units here. What units do we usually use for measuring charge?
Coulomb?
Yeah, that's coulombs. Strictly speaking, delta V is the voltage of the capacitor, the difference in voltage from one side of the capacitor to the other. But it turns out if we wait long enough, if we allow the capacitor to completely fill up as much as it can, then the voltage from the capacitor is going to match the voltage of the battery if we just got one single loop, because the battery is what's providing that voltage. But yeah, charge is measured in coulombs. And what's voltage measured in? Yeah, that's just volts. That is why we call it voltage. So that means capacitance is measured in coulombs per volt, which is known as farads. So 1 farad means 1 coulomb per volt. So if we describe the capacitor as having a capacitance of, let's say, 50 farads, that means that if you apply 1 volt of battery strength to it, it'll store 50 coulombs of charge. And 1 coulomb is actually a fairly, or 1 farad is actually a fairly large amount of capacitance. This capacitor here is marked, where was it? I don't know if you can see this, but looks like it says 3,300 microfarads. Is that right? Yeah, 3,300 microfarads. So that'd be 3.3 millifarads. I think that's right. In other words, about 1/300th of a farad. So about 1/300th of a farad means if you place 1 volt of voltage across it, it'll store about 1/300th of a coulomb. That is, you'd have to apply a 300 volt battery to get even 1 coulomb of charge. So 1 farad is very large. Any questions on that so far?
I was going to ask Casey, so the delta V in the Q equals C delta V, is that battery resistance or capacitance?
Technically, delta V is the delta V for the capacitor itself.
Okay.
Because each thing in a circuit has a certain voltage difference associated with it. If you take a look at the voltage right before and the voltage right after, those are going to be different values. So delta V is the difference between those 2 voltages. However, if you were to, let's say we ignore the resistor for now. Let's say we have just the battery and the capacitor hooked up directly to each other. The battery creates in this case, a 9 volt difference, which means not only this point, but this entire region of wire is all at 9 volts. Not only this point, but this entire region of water is all at 0 volts. So in this case, if you just have a battery and a capacitor hooked up to each other in a loop, then the voltage of the capacitor is going to be the same as the voltage of the battery, or the delta voltage, I should say. So that means that the delta V in the formula, strictly speaking, it is delta V of the capacitor. But in this case, if you just have the battery and the capacitor attached to each other, then the voltage of the capacitor will be the same as the voltage of the battery. Also, if you solve this for, because what we most care about is delta V. If you solve this for delta V, what do you get?
Do you mean like just in this specific example?
Yeah, just in this formula, you solve for delta.
Oh yeah.
Yeah, you get
Q over C.
Right, because we can just divide both sides by C. So that gives us a very useful formula for delta voltage of the capacitor. In other words, the more charge is stored on the capacitor right now, the more delta voltage the capacitor has, the more pushback it provides. And then the C is just a constant associated with that capacitor, the capacitance of that capacitor. And it turns out that the capacitance depends largely on things like how large those plates are, how close or how far apart they are, and also the material sandwiched between. If you have, like maybe you just have empty space in between, maybe it's a pure vacuum, or maybe there's some air in between, or maybe you have a layer of plastic or a layer of glass in between, some sort of insulator to make it even more difficult for charge to jump across. So the capacitance, there's a formula for capacitance that we're not really going to get into, but it depends on the area of the plates, how far apart the plates are, and the material, if any, that's sandwiched in between them. But the important thing is for any given capacitor, we're going to assume C does not change. We're going to assume C is a constant value. If there's 0 volts on one side, in this case, there wouldn't really be current flowing. If there's no resistor, then the capacitor essentially instantly fills up. But if there is a resistor, let's take a look in more detail about what happens if there is resistance. And keep in mind, the voltage itself is not what's important. When we say this location is 0 volts, that's just an arbitrary reference point. We could have called this 1,000 volts, and then this would be 1,009 volts. The name we assign to voltage does not matter. All that matters is the difference in voltage from one location to another. So if we have a resistor, if there's no difference in voltage, if this voltage is the same as this voltage, What does that tell you about that resistor? Right, there's no current. I wouldn't say it's shorted out in this case because we have a shorted out would suggest we've connected, for instance, this side and this side with another wire. So technically it's not shorted out, but it does have a very similar effect in the sense that we have no voltage difference. The before and after are the same voltage, and therefore there's no current. But this would be an extreme case. This would be if we have no voltage at all in the resistor. That means the capacitor is getting all 9 volts from the battery. And note that if the capacitor has voltage, that means the capacitor is storing charge. If a resistor has a voltage difference, that means the resistor has current flowing through it. So these are two important things voltage can do. Voltage applied to a capacitor causes charge to be stored. Voltage applied to a resistor causes current to flow. And so one very useful way to think of this circuit, if you've got a circuit with a battery, a capacitor, and a resistor, the 9 volts worth of voltage from the battery can do two different things. That voltage can cause charge to be stored in the capacitor, or it can cause current to flow through the resistor, or some combination of those. But if we write out the loop rule here for this loop of wire, one more thing before we do that though, as current flows, is the capacitor pushing in the same direction as the battery, or is the capacitor pushing back against the battery? Right, it's pushing back against, it's acting against the flow of, it's acting against the push from the battery. So to represent that, how do we represent the fact that it's a push back? How do we represent that directionality in the formula for delta voltage? Yeah, we use a negative sign. So generally we're gonna write, and not just for this circuit, but in general, we're gonna write delta V for the capacitor as negative Q over C. So let's try writing out the loop rule here. We've got this loop of wire. We've got 3 things in it. Each one has a delta voltage associated with it. So we can say the delta voltage from the battery plus the delta voltage from the capacitor plus the delta voltage from the resistor. Those 3 things form one complete loop. So what should their delta voltages add up to? Yeah, those have to add up to 0. Anytime you've got a complete loop, as long as you start and end in the same path, same point, I should say, if you go on a path that starts and ends at the same point, that path has to have voltage differences that add up to 0. Because we've returned to the same location, so we should expect to return to the same voltage. All state functions return to their original value. And we can fill in these formulas. Delta voltage of the battery is plus epsilon. Delta voltage of the capacitor is negative Q over C. Delta voltage of the resistor is negative IR. And I find it very useful in this case to add these negative terms to both sides to make the equation a little more comprehensible. If we add Q over C to both sides and add IR to both sides, we get I times R plus Q over C equals epsilon. And this is what I'm saying when I say that the battery can do these 2 things. The battery can cause current to flow through the resistor, or the battery can cause charge to be stored in the capacitor. Or it can do some of both, but it can't do lots of both, and it can't do none of both. Because the term with the current plus the term with the stored charge, those have to add up to this constant. So you might have lots of current flowing and no charge stored right now, or you might have lots of charge stored and no current flowing, or you might have some current flowing and some charge stored. But the important thing is these terms have to add up to a constant. An increase in one is going to result in a decrease in the other and vice versa. Any questions on that so far? So if we examine what happens in this situation as time passes, I think it's going to be very useful here to look at this as a couple of graphs. We can look at a graph of current as time passes and a graph of charge as time passes. And let's throw in some starting conditions. Let's assume we start with no charge at all. Let's assume the capacitor starts empty. If we've got an empty capacitor, so we're assuming charge starts off at 0. At that instant in time, you could plug in 0 for Q, and what would you get for I? If you plug in 0 for charge, what would you get for I, the current? Yeah, you plug in 0 for Q, this term drops out, then you can just divide both sides by resistance. So current is the voltage of the battery divided by the resistance. So that's the starting value of current, which we could call I sub 0. So the current starts off at this very strong value, this very fast current. In fact, that's exactly the current we get if there was no capacitor. An empty capacitor acts like just wire. It acts like it's not even there. With the capacitor empty, at that instant, it acts like just wire. It allows current to pass through with no pushback at all, because you get pushback if there's charge stored, and there is no charge stored yet. So right now, we get this fast current as if the capacitor wasn't even there. But as current flows, what happens to the capacitor as current is flowing? Right, it's going to charge up. We get charge building up. And since we have this very fast current, charge is going to build up very quickly. Be negative on the other side. So we get a very fast charge buildup. In fact, we can even establish a mathematical relationship between these. Q increases, yes, and the delta V capacitor also increases. With charge being larger, the capacitor is taking up more, is using more of the voltage of the battery. And since they're in series, they have to share the available voltage. More charge on the capacitor means the capacitor gets more voltage, so there's less voltage available for the resistor. So the charge is going to increase. And in fact, we can even establish a mathematical relationship between those, because how do we define current in the first place? What is current? Yeah, it's the flow of charge as a rate of change, charge per second. We can write that exactly as a derivative, dq over dt. Current is a rate of change. It's describing how much charge flows past that point per second, which means we can write it as a rate of change or a derivative. And what does a derivative tell you about a graph? Exactly, the slope. Since current is the derivative of charge, that means the value of current tells you the slope of the charge graph. We have a large positive value for current, so we should expect a large positive slope for the charge graph. It's going to be very steep. But more charge directly means less current because they have to add up to a constant. So we should expect the current to decrease similarly steeply. But now we have a slower current. Current is still flowing, so the charge is still going to be increasing. We still get more charge building up. But with a weaker current, we're going to expect a less steep increase for charge. Charge is going to keep increasing, but more slowly. Because current tells you how fast charge is building up. Slower current means less fast buildup of charge, a less steep slope. Of course, that charge increasing means more voltage used by the capacitor, so less voltage available for the resistor, so the current's going to slow down. But it's going to slow down more gradually. And again, we now have less current than we had before. So the charge graph is going to be less steep than before. Again, as more charge accumulates, the current gets weaker because the capacitor is using more voltage. So the current is going to be dwindling more and more, but also more and more slowly, eventually approaching what value? Yeah, after a long enough time, the current is never truly going to get to zero, but it's going to get close enough. So if we take a look at what's happening after a long time, we can assume that the current gets weaker and weaker and approaches zero. So we can say after a long time, and formally we're taking the limit as t approaches infinity. But in practice, a long time in cases like this often just means a few seconds, or at most maybe a few minutes. But these tend to decay very quickly. We can assume that the current is approximately zero. You plug in zero for current, and our new loop rule is just Q over C equals epsilon. In other words, it's the equation we would get if we had just the battery and capacitor with no resistor at all. Solve that for charge, and what do you get? Right, epsilon times the capacitance. So this tells you the maximum charge that builds up. That's the limit that this graph is approaching. The asymptote is epsilon times C, the voltage from the battery times the capacitance. And we usually call that Q max or Q final, because it's the maximum charge that builds up after a long period of time. So that graph is going to approach that asymptote, but never truly get there. So we get these very closely related graphs for the charge as time passes and for the current as time passes. Any questions on that so far? And what sort of graph is this? What function do we get here? Yeah, this is exponential decay. The current is exponentially decaying from epsilon over r towards an asymptote of zero. And the charge, even though the charge is increasing, this is still technically exponential decay because it's approaching an asymptote. In fact, you could think of this as what's decaying is the difference. Like right now we have this much difference between the value and the asymptote. A little later you have a smaller difference, and then a smaller difference, and then a smaller difference. So the difference is what's decaying as time passes, if that helps convince you that this is still going to count as decay. Yes, correct. It never truly reaches Qmax, it's asymptotic. Although in practice, we can say after a long enough time, maybe a few seconds, maybe a few minutes, it is close enough to Qmax that it may as well be Qmax. Like if this gets so close to Qmax that the only difference is a handful of electrons, then there's really no practical way you could tell the difference anyway. So we can say for practical purposes, after a long enough time, it gets close enough to Qmax that it may as well be Qmax. Likewise, the current never truly reaches zero, but after a long enough time, it's close enough to zero, it may as well be zero. And the important thing to notice there, if this resistor is, let's say this resistor is a light bulb, how would you be able to tell that there's current flowing through it? Yeah, it would light up. If the current is weak enough though, it's not lighting up enough to see. So if the current gets so weak that you can't see the light bulb, then for all practical purposes, you don't have any current, or at least it's not enough current to make a noticeable difference. So that's generally what we mean by after a long enough time. After a long enough time, the current gets so close to zero, it may as well be zero, and the charge gets so close to Qmax that it may as well be Qmax. And this is typically called the charging cycle. In the sense that we are charging up the capacitor. Any questions on that so far? And if we want to analyze this in terms of actual mathematics of exponential decay, let's take another look at that loop rule. We have I times R plus Q over C equals epsilon. And since I is just the derivative of charge, we can write this as Q prime times R plus Q over C equals epsilon. In other words, we have a differential equation describing how charge and its derivative are related. The problem is this extra epsilon here, this extra plus a constant makes things a little more complicated. In fact, this epsilon is really the reason why this graph is approaching epsilon over C, or epsilon times C, instead of approaching 0. But we can fix that by taking the derivative. If we take the derivative of both sides here, derivative of current is going to be, Q prime would be derivative of charge. So this tick mark, this prime symbol, is just a shorthand for dq dt. Or some textbooks use a dot over the variable. So in some cases, you might also see this notation, that a dot over the function means derivative with respect to time. In fact, some textbooks use dot as derivative with respect to time and tick mark as derivative with respect to position, because sometimes it makes a difference which one of those you're taking. But we're just going to use prime for both of them. So let's say we take the derivative of both sides. Current becomes derivative of current. And then R is just a constant, so we can leave it as it is. But for Q, what's the derivative of charge? What do we call how fast charge is changing? Yeah, that is current. Derivative of charge is current. And we also have divided by C. And then epsilon is a constant. What's the derivative of just a constant? Right, 0. So even though this epsilon can make things kind of complicated, by taking the derivative of both sides, we can get that constant to drop out. And this is now going to be much easier to solve. Specifically, if we rearrange this a little bit, because this now looks almost like the general case we were looking at for exponential decay earlier. If we isolate I prime, specifically subtract 1 over C times I from both sides, and then divide both sides by R. We now have a differential equation that's in exactly the right format. Specifically, it's in the same format as the one we were looking at the other day. The other day, we concluded from a whole bunch of calculus and algebra that if the derivative of some function is negative lambda, where lambda is just some constant, times the function itself, then that function has to be an exponential function. Specifically, original value times e to the negative lambda t. And you can verify that by taking the derivative of this and plugging it in, and you find that the derivative is exactly negative lambda times the original function. And note that that's exactly what we have here. We have derivative of some function equals negative some constant times the original function. So we can use this general if-then statement. We can say if the derivative of current equals negative some constant times the current, we can conclude that the actual formula for current as a function of time matches exactly this result, this conclusion. The original value, and note that we found that earlier, that was just epsilon over R, times e to the power of negative lambda t, where lambda is, in this case, 1 over RC. So we just get e to the negative t over RC. that is negative lambda times t. It's just that lambda happens to be 1 over RC here. So we now have an exact value for the current at any time. We can use this to predict the current at any time. We could now answer questions like how much time will it take for the current to reach 1/10 of its original value, or how much current is left after 10 seconds or something like that, just by plugging in numbers and solving for the variable we're looking for. Any questions on that exponential decay for current so far?
So Casey, to clarify, that equation that we just found is the equation for the IT graph that we drew?
Yeah, exactly. This graph, the function of the formula for this graph is original current, which is epsilon over R, times e to the negative t over RC. 1 over RC being the lambda value. And if you wanted to turn that into a formula for charge, we know the current is the derivative of charge. How do you undo a derivative?
Integral.
Right, you take the integral, and it turns out the integral of this is going to be this time, or divided by the derivative of what's inside, which just gets you an extra negative times RC. So if you take the integral, you're going to end up with epsilon over R times RC, because we're dividing by 1 over RC. One of the R's cancels out, we just get epsilon times C, also with a negative sign, times e to the negative t over RC. But also because we just integrated, we also get plus a constant. And it turns out that constant is just the new asymptote, which you can find by plugging in 0, 0, 0 for t and 0 for q. And you end up with that plus a constant being the asymptote, epsilon times c. So we could use this as a function to get the charge at any time. And note that that is also exponential decay with the same lambda. It's just got a different multiplier representing the starting value. And it's also got plus epsilon times c representing the fact that it's got a shifted asymptote. But since it still has the same RC here, that means both the current and the charge of this system are going to decay at the same rate as each other. In fact, what else does lambda tell you? What other information about the decay here could we get from that lambda constant? Yeah, you could get the half-life and also what else? Right, half-life and time constant, the two important ways of describing how quickly it decays. In fact, time constant is basically just the value you plug in for t to make this whole thing e to the negative 1. What t value could you plug in to make this whole thing just become e to the negative 1? Right, if you plug in RC for time, you get e to the negative 1. In fact, if you work out the units here, resistance times capacitance, that's ohms times farads. If you actually plug in the values for ohms and farads and simplify it, you get seconds. So R times C is an amount of time. And specifically, it is the time constant. If you replace T with RC, you get e to the negative 1. In other words, 1 over e. So RC is the time constant. It's the amount of time it takes for the original amount to decay to 1 over e, about 37% of the original. So the time constant for this RC circuit, this resistor capacitor circuit, is R times C. And it turns out that this is true regardless of whether you're charging it up with a battery or if you disconnect the battery, reform the loop, and allow the current to drain the capacitor. The discharging cycle also follows exponential decay, with charge decaying towards 0, but it's still going to have the same time constant, R times C. So large resistance means it takes a long time to decay. Large capacitance also means it takes a long time to decay. And then you could also convert this to half-life. The half-life is just going to be the time constant times logarithm of 2. In other words, R times C times logarithm of 2. So that's just another amount of time you could use as an amount of time where it decays a specific amount. And as a quick demonstration here, let me pull this up. What I've set up here is a circuit with a couple of batteries, a couple of buzzers so you can hear the exponential decay, a light bulb, so if that works, hopefully you can see it, and a bank of capacitors. I've connected these capacitors in parallel so they act like just one big capacitor. And I've got a switch here that can toggle between connecting the resistors, capacitors, and battery to charge it up versus connecting just the capacitor and resistor to discharge. So if I connect the capacitor, battery, and resistors, what would you expect to happen? If I set up a circuit very much like the one we were just analyzing, just battery, capacitor, resistor, what's going to happen in terms of current?
Well, the current's slowly going to go down.
Yeah,
right?
We're going to start with lots of current and then it's going to gradually decay. So watch and listen what happens there. So that's exponential decay. It started off bright and loud and then quickly got dimmer and quieter, but then hovered at that dim and quiet for a while. That's the lots of current quickly dropping to a little bit of current and then staying at a little bit of current for a long time. That in particular was charging. I was using a battery in that case. But if I flip the switch the other way, note that the capacitor is now charged up. These capacitors are storing lots of charge. And they can store it indefinitely. As long as you disconnect it and then just leave it, these capacitors can now store that charge indefinitely until I connect them again. So if I push it this way, it's going to connect the capacitor and the resistors, the light bulb and buzzers, with no battery. So this is going to be discharging. Shoot, that didn't work. In that case, the light bulb had come loose, which meant it was just the buzzers. Just the buzzers means less resistance. Sorry, they're in parallel. Just the buzzers mean more resistance because the light bulb wasn't an extra path. More resistance means it takes longer to decay. But if I keep the light bulb actually connected, here's charging, here's discharging. Note that it's essentially the same path for current, or sorry, same graph. Charging, discharging. It's the same general graph for current, even though it makes a difference between charge increasing towards an asymptote of epsilon over C versus charge starting at epsilon over C and discharging towards zero. But either way, the current is going to be the same graph. Technically, it would be flipped over because the current's going to be flowing in the other direction, draining the capacitor rather than charging the capacitor. But you get the same overall behavior for current, regardless of whether you're charging or discharging the capacitor. Because when we took the derivative, epsilon vanished, just turns into zero. So that means this differential equation and the results are valid regardless of whether you're talking about charging or discharging. So for current, it's going to be the same behavior whether you're charging it or discharging it. For charge, it's the difference between starting at zero and decaying towards a positive asymptote versus starting at a positive value and decaying towards zero asymptote. But the current behavior is the same. Any other questions on that so far? For discharging, technically the current would be negative. We usually treat current as an absolute value, so it doesn't really matter, because the light bulb doesn't really care which direction current's flowing anyway. But technically the discharging cycle would be current starting at negative epsilon over R and decaying towards zero. In practice, that usually doesn't matter because it's still current flowing through the light bulb, so the light bulb's still gonna light up. But there are some circuit elements that only allow current to pass through in one direction. And we would treat this as negative because in the discharging situation, the charge is decreasing. So we treat current as negative because the current flowing is causing a negative change in the amount of charge. It's causing a decrease. Any other questions on that? All right, then I will see you next time. You're welcome.